The next speaker is Mike Norman from Argonne, and he's going to tell us about quantum Hall superconductivity.
All right, get the honor of the last talk. So let me start. I don't have a picture of Allan, but I do have a picture of Cy. This is some conference back in mid-'80s at Argonne. So this is me, and on the other side is John Perdue. This is sort of the first connection, because if you heard yesterday, Cy decided to send Allan, when he was a graduate student, down to Argonne to learn band structure from Dale Colling. And of course, at the time, John was a postdoc with Cy and got the ideals. So when I came and become a graduate student at John's, he's like, okay, I'm going to send you down to Argonne, like Cy sent Allan. And the only difference is that Allan realized it was a visit. He left. I never left. So here we are almost 42 years later, and I'm still there. So the project I want to talk about, how it started, was the following. So high-TC was discovered in '86. NSF decided to run a competition for science and technology centers and superconductivity, and we got one. And you should have heard the howling, right? So a lot of you out there have DOE grants. Okay, you're at the lab. Sometimes it comes out of our hides, but we're good about it. But Lord forbid somebody from a national lab gets an NSF grant. Oh my gosh, the pitchforks came out. So it was like an experiment NSF did once and they didn't do afterwards. So it was a consortium of 3 universities in Argonne. And as part of this, we had a visitor pool of money. And at the time, Allan and Steve were at Indiana. And I said, Allan, why don't you come for a visit? I have a project in mind. And so the project has to do with the following. Quantum oscillations have been seen in type 2 superconductors, which is a bit bizarre when you first think about it, because you think superconductors have an energy gap. Why would they have quantum oscillations? And in fact, if you Fourier transform the data, as you see in the upper right corner, the period is the same as the amplitude is suppressed. So if you do a standard Dingle plot, the solid line is a Dingle, the plot from the normal state, from which you can extract the Dingle temperature, which shows the broadening of the Landau level. And this is the x-axis in terms of 1/b. So when you go to the superconducting state, you have this extra suppression, right? Relative to the normal state. So that's the only thing. Period's the same. It's just the amplitude is suppressed relative to the normal state. Okay, so this thing had originally been discovered by Graeber and Robbins and iodine diselenide, and there were a lot of semi-classical studies done by Kazumi Maki, Mike Stephen, and others. But the influence of Landau levels on superconductivity probably goes back to this paper of Grunberg and Gunther in 1968, where they not only talked about effective quantization in the semi-classical regime, but set above the semi-classical HC2, because you have these spikes in the density of states, you might have reentrant superconductivity as a series of spikes extending above the semi-classical upper critical field. Okay, and so Mark Result, whose name came up yesterday as well, another Toronto person, and Zlatko Tozanovic did a Review of Modern Physics article on this, and this is sort of the phase diagram on the left. You have the semi-classical regime at low fields, and then at high fields, you have this potentiality of reentrant superconductivity due to Landau level quantization. And the thing on the right is some paper I did in 1990 showing, of course, that as soon as you lift, so the assumption here was the Landau levels were degenerate. And as soon as, of course, you start lifting the degeneracy, say with a Zeeman term, of course, the effect gets rapidly killed because you kill the BCS log when you do that. And I remember after this paper came out, Zlatko was visiting, and I think Zlatko maybe a year, 2 years older than me and he just basically said, look, son, I have some advice for you. Don't be on the wrong side of history. And the wrong side of history was that this phase was going to be discovered, and the people who are advocating it, would become famous as a consequence. So as you notice, all this was sort of these semi-classical type treatments. But if you go to the quantum limit, you have some interesting things. First off, TC is proportional to pairing interaction. This is something that's now been rediscovered in the context of flat band materials, unlike the exponential relation you have in BCS theory. But you have to have sufficiently high magnetic fields to get in the quantum limit. You need, of course, minimize Lano level broadening or any effects that would broaden out Lano levels. You, of course, need to quench the Zeeman splitting. And one way you can do this in 2 dimensions is by tilting the magnetic field. Since you tilt the field, that changes the cyclotron splitting, but doesn't change the Zeeman splitting. And then, of course, the big thing is that there's no other competing states that intervene, like Chern insulators or what have you. Okay, so Allan's visiting and said, forget all this semi-classical stuff. We will do the problem exactly. And so typical Allan, he disappears in a room. A couple of days later, he comes back with these beautiful notes. They're probably in my office still somewhere. Blank sheets of paper, beautiful writing, where he solved the problem. And what he realizes is that he sets up the Bogolov-Dujan equations in a Lano level basis and shows that the matrix elements in the Bogolov-Dujan equation is analytic, derives these analytic things, and said the self-consistent solution of these equations by staring at them as a vortex lattice where the pairing kernel is diagonal in the vortex lattice momentum. That is essentially you're pairing K minus K in the vortex lattice, except it is not a diagonal in the Lano level index. And so the secular matrix becomes 2n by 2n. The 2 is from particle hole. And the n is a number of Lano levels involved in the pairing, which, of course, in the semi-classical regime could be many, many Landau levels, right? And particularly, he took a look at and in this paper that we did with Hiroshi and Steve, if you look at the quantum limit, you can get some interesting vortex lattice solutions. This is for the n equal 1 Lano level. You can see that you get a doubly quantized vortex, and with positive and a singly quantized vortex with a negative. And that means that these states can have potentially interesting topological properties. Of course, nobody was talking about topological properties back in 1991. And so you can run these equations. We did some paper that we had to dump into Physica C because of referee B. I don't go further into that. And this was designed on the left for some high TC material based on BISCO. Semi-classical upper critical field was order 50 Tesla, and then the prediction you would have these things going up if you could maintain Lano level degeneracy. Then in the semi-classical regime, you can look at the order parameter. So on the right is versus temperature. So if the bottom is near TC, and you get, this is the order parameter, you get sort of the Abrikosov type solution. And this is because it's basically the solution sits in the n equals 0 Lano level for bosons, which is basically the center mass channel for the pairs. But as you go down in temperature, you can mix in these higher level Lano levels, and because it's hexagonal symmetry, you mix in n equals 6, n equals 12, and therefore you get distortions of the order parameter due to these admixtures of higher Lano levels as you go down in temperature. And then you can do the same thing at low temperatures by varying the field. Again, these admixture changes as a function of magnetic field. Interesting thing is it has non-trivial band structures. So this is a plot of the eigenvalue dispersions in the vortex lattice phase. And now you can understand why you see quantum oscillations, because effectively you have near gapless behavior in the vortex lattice phase. And that's a typical plot is shown on the left. In the middle, this is the average energy versus the Landau index, which is demonstrated when it's flat at high Landau index. It means you're at high fields and the states are basically Landau levels. At low fields, you see this variation, which is just the fact that these are Caroli-Dujan matricon states. So what happens is the vortex core bound states you get in semi-classical theory evolve into Landau levels as you pump up the magnetic field. And then if you just take a numerical calculation, all the eigenvalues in the zone, and you plot them as a function of field, you will see all these zero crossings. And of course, again, we weren't thinking about topology at the time, but obviously these zero crossings are a series of topological phase transitions that was revisited by a student of Allan's, Gaurav Chaudhary, back in 2020, and was, quote, rediscovered, unquote, by Lang Fu and Leon Glasman in a paper, archive paper that was released earlier this year. Okay. So after we did all this stuff in the 1990s, I'm sitting there thinking in my back of my mind, is Zlatko right? Is there something out there? And the problem with gallium arsenide, of course, is number one, it's not a superconductor, and number two, the G factor is low. So tilting the field and getting Landau levels to come in coincidence is not going to work. But when magnesium, zinc oxide heterostructures came out, it's very interesting because the G is near 2, and people have been doing tilted field experiments where you can bring Landau levels into coincidence. So I thought, okay, that's great. The problem is this thing is not magic. It assumes that superconductivity is already there at 0 field. And of course, these heterostructures are not 0 field superconductors. So I said, well, that's too bad. The other thing we were worried about at the time was that pairing might happen, but maybe the superfluid stiffness would be 0 because you quench the kinetic energy in the Landau levels. Now we know from recent work that because of quantum geometry can come in to save the day. That is, you have matrix elements to remote bands. This can cause a minimal value of the superfluid density that's finite. And maybe that comes in and saves the day. So I was like a lot of people. I was at 2018 March meeting. Pablo gives his talk. I'm thinking, oh, wow, maybe this is it. Superconductivity with high TC over EF ratio, quantum limit can be easily reached. Landau level degeneracy seems to be present from what you see in their Landau fans. So I said, this may be it. So I dug out the old codes from the 1990s, ran it, looks promising. The problem, of course, is what we did back in the 1990s was a single parabolic band, which is, of course, not the electronic structure of twisted bilayer graphene. And so this is where Guarv came in. Guarv did something which I thought was qualitatively different. He took the formalism of the 1990s and generalized it to the multiband case. And the model we did was we had a model that we came up with that was designed to expand around the insulating state at -2 filling. And depending on the parameters of the model, you either get a Trivoli insulator on the left, you get a valley churn insulator in the middle, or you get a churn insulator on the right. And then this is a resulting Landau level spectrum. The blue arrows are in the plus valley. The red arrows are in the minus valley. And then what you do is you basically look at these things, and because you have Landau level degeneracy in this case, you have a degeneracy 4 that's been lifted and now becomes a degeneracy of 2, you can have pairing. And so when you run these calculations, this upper right, the trivial and churn case looks promising. That is, you get TCs at 10 Tesla that are, at least in mean field theory, bigger than what you get for the 0 field TC. The red curves are what happens if you put a dingle temperature in that we estimated from Pablo's data. And that, of course, suppresses things because of Landau level broadening, but prediction is you still get TCs of order 4 Kelvin at reasonable magnetic fields. The valley churn case is different because it's unusual. The lowest 2 Landau levels break valley degeneracy. And so you cannot pair. We were assuming intervalley pairing, and you cannot pair in that case. And so you don't start to get pairing until the n equal 2 Landau level. And these matrix elements typically get suppressed as you go to higher and higher Landau index. And so by the time you put in something like a dingle temperature broadening in the valley churn case, you sort of killed the effect off. Okay, caveats. Is Landau level degeneracy really present? Sometimes it looks like it's there, and sometimes it doesn't look like it's there. You need degeneracy, because if you don't have degeneracy, any degeneracy splitting actually kills a BCS log rather rapidly. What about the effect of the lattice potential? So the problem, of course, we know from work that Dima Efetov and others done, by the time you get in these field ranges, Hofstadter physics becomes important, and that leads to broadening of Landau levels. And the other thing is you lose out, right? That energetically, you could predict a superconducting state, but a churn insulator might have a lower free energy. And the last thing, of course, is a superfluid stiffness really finite or not. That is, if there was pairing present, would you be able to see it? And there's a variety of groups, including Dima's group, Andre's group, Janindra Jain's group, and there's even a paper by Sankar on the bottom. Maybe Sankar's left by now, but Sankar, you're there at the bottom, looking into some of these matters. Okay, unfinished project. which is what I'm going to conclude with. So when cuprates were discovered, people were like, is there a Fermi surface there? And eventually on the overdope side of the phase diagram, where you would predict a large Fermi surface as in band theory, this was eventually seen. Very tour de force measurement, thallium-2201. You don't see quantum oscillations to get to very high fields because the enclosed area is large. But in the underdope regime, starting with Louis Taillefer's group, people saw quantum oscillations, but they indicated some kind of reconstructed Fermi surface. That in the pseudo-gap regime, you had a reconstructed Fermi surface, and the leading explanation was probably some density wave state. And so various people, I did a paper with Andy Millis, there were other people, and the leading explanation is that you have some sort of biaxial density wave state that potentially explains these pockets. But there are also some technical issues, I mean, as far as getting that those calculations to actually agree with the data. And the other thing to realize is these are experiments by Suchitra Sebastian's group. If you go to very high fields and low temperature where you see quantum oscillations, there's definitive evidence in the data that you're still in the vortex phase, even when you're going up to fields of order 50 Tesla, which is where, and quantum oscillations are typically done from about 20 Tesla up in these materials. So you're in some sort of vortex matter phase when you're doing these measurements. And therefore, what had come about is that possibility where you're getting quantum oscillation for a paradensity wave state. So one of the theories for pseudo-gap phase is you have a paradensity wave phase where you're pairing electrons with a finite momentum. So it's not zero momentum like BCS, but it's at a finite momentum. And to contrast this, you have a series of orbits in real space, and this is a network model of Papards, right? And on the left is a standard one where you have a series of electron orbits, and what you get is these lens orbits. You get, if you don't have magnetic breakdown, you get either open orbits or you get this lens orbit, right? And then when you get high enough fields, you get magnetic breakdown where you recover the original Fermi surface of the unreconstructed state. But if you go to the particle hole case, and what happens is on the upper guy, the arrows reverse, and instead of getting this lens, you get a dog bone instead, which is shown on the middle plot. And of course, if the gaps are large enough, this dog bone is well defined, and you have to go to high magnetic fields to get breakdown. So the ideal is, yes, you could get something that has to do with some kind of thing that looks different from a density wave. So in the density wave, you would get the lens. In the paradensity wave case, you would get the dog bone. And you could do more sophisticated calculations. These are calculations I did for a uniaxial paradensity wave on the left. And you have a series of dog bones. They're colored in red and blue because the red orbit is a hole orbit and the blue orbit is an electron orbit. And for some different reason, in the biaxial case, I colored it differently. The electron orbits are in green and the hole orbits are in red. And the arrows simply is just a spanning vectors across the original normal state Fermi surface. So you get these nice pockets here on the right that look quite a bit like what people try to get from the de Haas and Alphen data. And then Seamus Davis and I wrote a paper about this back in 2018, like, okay, let's take a model of cuprates, let's do it. And you get a lot of stuff that looks similar to the data as a function of the gap size. The gap increases as you underdope. You should have a Lifshitz transition where you go from electron orbit to hole orbit. Because of that, you should have a mass divergence. And this mass divergence has actually been seen in experiment. So we thought maybe this is what's going on. And then along comes Patrick and Sentel, and they said, no, 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 no. You're thinking Onsager, and you're assuming Onsager is right. And it may not be the case. So you think about it in real space, Mike, you're doing a cyclotron orbit, and then you do Andreev reflection. And now the electron reverses, the thing reverses, and so you never have closed cyclotron orbits in real space, and therefore the Onsager relation breaks down, and you should not get any reconstructed period. The only thing you should see is magnetic breakdown at high fields that recovers the original Fermi surface. And Dwar Orgad's group tried to do numerical simulations, and that's what they find. Here's a dog bone in red. They don't see the dog bone. All they see is original circular Fermi surface in their calculations. But again, these are semi-classical calculations where a series of approximations have been made. And when they do this, this is what they get. And the question is whether it's right or not. So I did look at the semi-classical thing. This is again Papard's network model, but now I have the electron orbit on the top. I have a whole orbit on the electron orbit on the bottom, a whole orbit on the top, and then you do this kind of thing where you see as the electron goes around the cyclotron orbit, what's the phase accumulation and what kind of area does that correspond to in momentum space. And if I make assumptions about the scattering matrix elements at these points R and R prime, whether you get magnetic breakdown or you get Andreev reflection, and make it again what I thought was a realistic assumption about the gauge transformation as you go from one orbit center to the other, which is different in this case than in Papard's case. When I solve this on the bottom and look at the allowed eigenvalues, I only see this combination xi plus z, and in Onsager relation, this thing corresponds to the original Fermi surface. So maybe these guys are right. You only get the original Fermi surface, as opposed to the electron case that Papard did, where you see this thing on the bottom, which is the lens area. So I said, well, maybe these guys are right. So Gore's attitude, no, we do what Allan would do. We solve the problem exactly. We do numerical simulations for pair density wave based on Bogolov-Degen and Allan level basis. And this is challenging because you now have two length scales in the problem. You have the magnetic length scale, but you also have the inverse of the PDW wave vector, which makes things far more complicated. But if you do this, and he did two cases, he varied the PDW wave vector. So the reconstructed Fermi surface in one case looks like on the left, and on the right you see something like the dog bone in the middle. And he Fourier transforms, and he gets periods that doesn't look like any of these things. The closest it looks like is a period is half that. So on the left, the period looks like half of the oval orbit in the middle. On the right, the period looks like half of that of the dog bone. What's going on? Worf moves to Cambridge for a second postdoc position. Mike, no problem, I'll finish the paper off. Boom. 2 years have passed. So I was hoping because of Allan's thing, you'd be here, I could chastise him in person. But he's not here, so unfortunately. So what is it's certainly unpublished, and I have to leave it as question at the moment. So let me summarize. Quantum oscillations occur in type 2 superconductors. It was sort of a surprise when it was first observed. Reentrant superconductivity to Landau level quantization is possible, but to date has not been observed. In both regimes, above and below the semi-classical upper critical field, there are non-trivial topological properties that are present in the vortex phase. Quantum oscillations, or their lack thereof, due to reconstruction by a pair density wave state, is still an unresolved matter. So with that, let me conclude. And it was a wonderful conference. Thank you all for inviting me.
Any questions for Mike?
In the work you did with Seamus Davis on the Coop rates,
Yep.
you said there was a divergence which has since been observed. It wasn't clear to me what you were referring to that was
So if you look at the
diverging.
quantum oscillation data, right, as you go towards the overdote regime, the effective mass diverges, right?
Okay, effective mass.
The
Got it.
effective mass diverges.
Yep.
Yeah. And so that would be consistent with the Lifshitz transition, which of course is what this theory would predict. That
Yep.
As the
Thanks.
Any more questions?
I think theoretically this is all pristine and very nice.
Yep.
But the problem that I see, of course, there is always a but, otherwise I would not ask, is that it's occurring from a peak in density of states, which is very sensitive to disorder, meaning
Yes.
the typical Anderson theorem is irrelevant here. You know, I mean, Anderson's theorem would not apply in a bulk metal,
Yeah.
disordered suppressed density of state, because that just in the exponential. So I think the observation of it would require very pristine sample where the dingle temperature is very low.
Yeah.
It's not just enough for mobility to be high.
Right.
Okay.
Right. And so, like I said, the things we did, we took a dingle temperature from Pablo's data. Dingle temperature is too large, you kill the effect. If you lift Landau level degeneracy, you kill the effect.
Yeah, this is like a well-known secret in 2D system,
Right.
that mobility temperature and dingle temperature could differ by a large factor in
That's
many
exactly
situations.
right. And of course, the other issue is the following. This is all mean field theory. So there's some underlying assumption that vortices are pet, because as soon as you have dissipation in the system, right?
Yeah, I used to have these reservations of mean field theory, but great Allan MacDonald convinced me. Mean field theory rules.
Okay, well, there you go, Alan. Mean field theory rules, we're safe. So, thanks a lot.
Maybe do one more question.
Is
Mike.
here is the reentrant superconductivity under high magnetic field in uranium telluride relevant? That there's a superconducting island, right? Appears above
So here's
40
the
or 50
problem,
Tesla.
The reason this works in twisted bilayer graphene is the quantum limit is very low. This has now been seen by beam methodology. You've been able to see the quantum. Okay. So and the point is, if you take any ordinary material with a normal size Fermi surface, the quantum limit is basically not achievable, even at the maximum. So that's the first thing you have to understand. Because in the as Alan showed, the Perry matrix elements in this reentrant regime decrease strongly as a function of Landau index. So to get any hope of seeing it, you want to be at a small Landau index.
Okay, thank you again, Mike.